Hey, and welcome back to Numerical Analysis. Let's balance out some lighting here. There we go. Slightly better, and we can do a little bit better. There we go. So welcome back to Numerical Analysis. So so we're just past the first exam, and we have our project coming up. And lighting can be a little bit more balanced. How's this? That works, right? Anyway, so that's what we have coming. We have on Thursday, our first project is due, and I haven't really. I've told you what to do, but there's still a little bit left that a lot of you feel kind of nervous about. Is how do you actually deliver the final product? The short answer is adds a bunch of M files, and I basically want to be able to push play and see a bunch of plots, and that's it. I'm going to show you here in this video the sort of thing I'm looking for. I am coding this up in sort of the most boneheaded way I can. Not expecting this to be super efficient. I know a lot of you guys haven't coded at all, and since this is all new experience to you guys, I'm just showing you guys a really simple way of putting this together. In the future, we're going to start practicing proper function calls and doing all that. If you found this MATLAB material hard to do and to keep up with, it's really something you should be coding up as you watch the videos. So every video I post, when you're watching it, you should basically throw up MATLAB as it's running and code it as I go along. And that's probably the best way for you to actually learn, because the only way you can really learn how to do MATLAB is to do it and just jump into the code and start practicing. Things will start coming to you as you get more and more involved in there, but it's not going to happen unless you actually deliberately and methodically go and try to do it. And so the reason why I code up those videos for you guys live and not just giving you whole code snippets is not for entertainment's sake, but to give you an opportunity to sit down and code as you watch. Now, what I've asked you to do for these projects is very simple. It's just modifying my code a little bit and then pushing play. And I'll show you the sort of modifications you need to make on, say, the Taylor polynomial one. There is one thing I asked you to do, which was the coding up Lagrange interpolating polynomials, and that might be a little bit of a challenge, especially if you haven't done the other things. If you can't get that working, that's fine. Just go ahead and put the Van der Waals interpolation code in its place. It'll give you the same polynomials, but you will get docked a few points. The idea was for you to go ahead and code that up, but it is going to be something that kills your grade entirely. So that gives you, so this is going to help give you an idea of what I'm expecting when you submit it, and yeah, so then we can go ahead and do that. Let's see, other business, yeah, maybe that's a good place to stop. In the future, we'll have, we'll be getting more and more of these projects coming along faster. It's taken this long to do it because I want to give you guys an opportunity to take your time in learning MATLAB. And so we're about halfway through the semester having the first project due, which means that the other ones are going to be coming up a little bit faster than this. But now, hopefully, after this project, you'll have a better idea of how everything goes down, and yeah, and you'll be able to respond faster. I guess, yeah, I guess we should just go ahead and jump into it. Okay, so now we're just gonna go ahead and jump into this. So I've coded up a few script files that'll like segregate everything. It looks like a lot, but really it's just like straight calls of code that I've already given you. I'll show you how to modify the Taylor polynomial code to fit the things I was asking you to do, and yeah, and then other than that, I'll just show you the sort of things I'm doing to modify my code in order to make calls for various things. Now, in the future, we will want to code all this stuff as like proper function calls, but for now, I'm just calling them scripts. And so you can call a script just by writing down its file name without the .m, and MATLAB will run it. So if we go ahead and take a look, what we have here is my sine script, but in the main file, this is one that I'll probably be looking for from you guys. Basically, I have 2 of them done already, and so there's a square root and the sine, and if I push play, it's going to give me a whole bunch of plots. It's total of 12 plots here, and I didn't put the title on this one, but this is the plot for the sine derivative, and so it's not just sine; it's like sine plus cosine, some combination of these guys, and so it's plot there, and yeah, and then these plots actually don't end up looking very interesting because these are very high degree estimations that actually perform rather poorly. If you zoom into these, you'll actually start seeing something a little bit more interesting. Let's see. Zooming in, there we go. So, the original function here is in blue, so that is this guy. And so everybody should match up roughly around here. And so you're seeing like the Taylor polynomial and all that stuff, it matches up fairly well, but then Taylor polynomials just make this dramatic change where they just start going way off kilter. And so ultimately nothing else looks like they matches up very well. And so you really can't see the progress of everybody else because of Taylor polynomials. We can zoom in to just see our guys. If you just drag straight down on your zoom command, it'll allow you to zoom in to everything else. And these guys look like they're matching up a little bit better. So we have polygons of degree 10, so we have 10 interpolation points, or well, 11 interpolation points. And Bernstein polynomials again is actually using 11 points, and etc. Let's see, the original is this blue wavy one here. Bernstein and interpolation, actually they're both unfortunately they're both red for some reason, but you can tell that this is the Bernstein approximation because it's not actually interpolating into points, and Bernstein polynomials aren't meant to. And you see it's having trouble matching up with all these like crazy variations here. But the interpolation, the actual interpolation here, it's doing okay. It's kind of keeping up, but it's not perfect. And so that improves with higher degrees. And then even at degree 2, Taylor polynomials are way off on this interval, blowing up way over here and here. But yeah, so and this bumpy one's the original function, and everybody else, it's an interpolation of polynomial degree 2, and so yeah, it's not doing very well either. Yeah, so roughly this is something that I'm looking to see, and this is for the square root function. The derivatives are given here, and then for the other ones we have square root being approximated both over 0 to 10, but then after this we're going to start seeing the 1 to 2 interval, and so not a lot of interesting stuff here, but it's done. So let's take a look at what is actually inside of square root script. So if you take a look in here, I did a loop in this point just so I don't have to keep repeating the code over and over again. You don't have to do that if you just want to, just put the same thing over and over again. That would be fine. Although you can see how to do it here. I just put the degrees of the polynomials I want, and now I'm just running through those polynomial degrees. So A and B are my endpoints of the interval I care about. And so 1 is being on the left side, 2 is being on the right side in this case for a square root function. And then so then I define f as being my square root of x. This is uniformly used in the other code that I've given you, and so that hopefully you can just sort of like delete the definitions in there and then just declare this when you need it. So then I start a figure, and that's where I'm just going to start piling on each one of these plots. I define my sampling domain to be, or not a sampling domain, but my plotting domain as just being t going from A to B, and I have it at 0.1 in segments. So, and then y is f of t, and so yeah, so that is basically these two guys. We can make a plot. Now here I actually put what is called a label for our legend, and so it's the display name for this plot, so that later when we call the legend command, it'll actually put this match the color with this name and give us a little legend on there, and so that'll be handy. And we want to keep this plot active, so we say hold on, so we can add more plots to it later. So then I select my polynomial degree. If you wanted to just write this explicitly, we can put like 10 or 15 or 2 here, and then that's going to give me my polynomial degree. And so then I put a title on my figure. This only works if you put it after the first plot. That's why it didn't show up on the other one, because I forgot to do that. And so since we already plotted something here, we can now put a title on it. And so I'm saying this is square root of x over the intervals 1 to 2, approximation degree, and then I put plus n after the quotation mark. You have to use quotation marks here. If you put single quotes, it's going to take those as like actual like a vector of characters rather than a string, and that's actually pretty common in programming languages. So a string is just basically a collection of text. Then here I say I want to do interpolation. Now I'm just using my Van der Waals code, but I would like you to do the Lagrange polynomials, and then I'm out of there I get z, and if you look at the code that was given previously, z is actually the output of the polynomial. So I'm just saying, okay, now plot what we just got, and we're going to give it a display name. We're going to call it interpolation. And I said keep holding it on because I have more to put here. So now I go on to the Bernstein polynomials. Again, z was used as the same variable there, and so then basically you have a display name and Bernstein, and so same thing. It's just put another plot in there and then put hold back on. And now we're going to go to Taylor polynomial. Now Taylor is a little bit different. We previously had f in there. I'm replacing f with another variable name, simf, because we need a symbolic variable. And above, we actually had declared f being this, which is not a symbolic function. So then I declared a new symbolic variable, sx, for symbolic x, and then a symbolic f. I declared as square root of s times x, sx, and then I called my Taylor series, and I'll show you what that looks like in a minute. Then what do we get? The output of Taylor series that corresponded to polynomial is actually this vector y, so I go ahead and put that in, and I give it a display name, Taylor. Now here I gave it this G, that means it's going to be green. I'll just let MATLAB figure out what color that is, so I'm deleting that. We're going to delete this too, so we stop having both two plots being red, which is awkward. And I'll let MATLAB figure those out. We don't have to put colors on them, so we know what they are because we already put labels on them. So then they'll show up in legend. And then in here, I am now doing the polynomial. That was another thing I asked you to code up. This only takes a slight modification of the interpolation for the Van der Waals matrix, and so I made up a new script that I'm calling derivative by interp, and so it's a derivative estimation by interpolating polynomials. And here, a to b, again, same t. You have to define f prime if you're going to test how good your derivative is. You need to know what the actual derivative is. And so, so then I go ahead and define that. And so then this is to plot the derivative. And so then I go ahead and I plot that, and I call it the true derivative. Okay, not too bad. And now I go through a loop through all the polynomial degrees that I defined above. And yeah, I just run this again. And each time I increase it, I tell it to put a new plot, hold it for the next, and I call this degree plus n. Again, I'm using quotes here instead of apostrophes because this is a string, and I want to add a number to it without actually, which basically just adding a string to the end. So, in any case, so yeah, so then I give it a title, which happens after the plots, and I'm calling this square root of x over 1, 2 derivative approximation. Now, I continued this here, and this is just for the next portion, is square root of x over 0 to 10 rather than just 1 to 2. But same deal all the way down. And that we don't need. Well, there you go. And whenever you finish with a figure, make sure you call legend in order to make it put that little legend box up there. So let's run this, and it should give me 8 plots altogether. Yep. So this is the derivative for 0 to 10 approximation. And so this is coming from interpolating polynomials, and so this is interpolating polynomial degree 2, degree 5, degree 10. Honestly, that degree being 2 is looking a little bit off to me. I think I have an off by 1 error, and so since I see this as a straight line, I should probably go back in there and edit that, but I'll do that later. Well, actually, if it's a straight line and it's a derivative, then actually that's probably fine, right? Unless it's a constant function. So again, I need to go back and maybe fix that. But anyway, so here we go with more approximations, and yeah, this one didn't do a very good job, and again, I'm guessing that is because it's actually a polynomial degree 1, so I keep getting something constant here, which is odd. Yeah, so here we go. That is that. And now let's go ahead and take a look at what I did for Taylor series to give you an idea of what I adjusted. So if I go ahead and open this up, the Taylor series before had degree of polynomial, and we're already declaring that as being n. So since we wrote n back in the square root script here, and then we later called Taylor series here, we're just going to use that n in particular in there, so we're keeping that variable still alive, so I can use it up here. So I'm putting n inside the degree of polynomial, so that was declared outside of this code, but it's still relevant. I'm putting a note here that I'm assuming that there is a symbolic function simf, which we did define in the previous code, and then there's a center a, which is given. Okay, so here's where the degree of polynomial goes. So that's where the n went in. Again, it was something that was given. And here I had declared a as being 2, but since it's already given, I'm just commenting this out, so it's not going to be executed. But I did notice there was an error in my code last time. I had t minus 2 here. This should be t minus a. So make sure you edit that whenever you go back to do the Taylor polynomial. In any case, I think that's all the adjustments I needed to make here. I changed all the calls to f to simf, which if you want to change something, you say like hello world, you can just press shift and enter, and all instances of that simf is now been replaced with hello world. But I wanted to keep it as simf, so I changed it back. And so that's a really easy edit, so you can just highlight f, replace f with simf, and then shift enter, and then ta-da, that's done, and you don't have to worry about missing one. I deleted all the plotting stuff because we're going to do that later, and yeah, and that was all the edits you need to do for the Taylor polynomial. It's actually rather simple. And so then back over here, if you want to call the Taylor polynomial stuff, it's really just this. Let's go ahead and I'm going to evaluate it, and it gave you something. Now, all of this might look like a lot more, but really if you look at it, it's only about plot the figure for the original function. Okay, what is the degree of my polynomial? Make a title. Call the interpolation code, plot it. Call the Bernstein plot it. Call the Taylor series stuff, plot it. Nice and simple. So, and then that's one of them done, and then you just copy and paste this, and you change when you go to say sine. So the sine script, same exact stuff, except square root of x is changed with the new function, and I also had to change it for the symbolic function too. And then change the bounds, change the center that we're calling with, and that's done. And then you do that for sine, square root in 2 different cases, and then also the exponential function. And so it's actually not too bad. Like I said earlier, if you can't figure out the interpolation with Lagrange polynomials, that's okay. I mean, of course you will lose some points, but if you just want to get something working, you use my interpolation code, and you'll have to make some edits there. But yeah, it's not too bad. There's the Bernstein polynomials took like maybe 2 edits to the entire code that I gave you. You just have to make it so it'll work on any interval a, b. Right now it only works on 0 to b, and so you need to be able to figure out how to shift that wherever you need to. But that's really just ultimately it ends up being a like high school algebra problem where you're just trying to match a linear function. So basically you're trying to send the interval a, b linearly to 0, 1, and that's that. And yeah. It's late. It's well past my bedtime, and yeah. Didn't do the full MATLAB at midnight just because I didn't have the energy to set up, and it's easier to record from my office. I'm trying to think if there's anything else I wanted to mention. But yeah, basically what I'd like for you guys to turn in is basically something that's like this main M file where I can just open it up and press play, and the 16 figures that I should have pop up. Here, let's go ahead and make an exponential script while we're still thinking. And yeah, so I'm just going to copy the sine script and copy and paste. And X script. And now let's go ahead and make the changes there. And so basically we're changing this to the exponential function of x, and this is going to be the exponential function of sx, and the interval for that one, let me see if I can find it. There we go. The interval for that one was 0 to 5, and Taylor polynomial is centered at 0. So, so then what are we going to have? I'm going to say this should be 0, this should be 5, and here is 0. Already is 0. Right, and change the titles. Say exponential function, and have display name exponential function, and this should be moved after the first plot at least. So okay, so then that's done. We can test that real quick. What do we get? There we go. We have a few estimations. I don't know what's happening with this guy. Oh, that makes sense. I didn't actually change this one and the derivative to be an exponential function. So the derivative exponential function is just the exponential function. So that's all I need. And so let's go ahead and test it out. Good. Again, I think I have an off by 1 error, and so it's something that's easy to correct. And yeah, but otherwise these are sort of plots I'm expecting to see. So here I had a polynomial degree 30 for approximations. I wasn't very specific with it, with the polynomial degrees. I really just want you to pick polynomials that really demonstrate improvements in the approximation as you increase the degree. So start with something really small, like degree 2, and then go up to degree, 10, 20. Whatever you feel is sufficient to show that show improvements in the. And even if there isn't improvements, that's good to show too. Yeah, so I think 20 should be sufficient here. And this is the exponential function over, what was it, 0 to 5? Yeah, and cool, yeah, I think it's good. So, so then if I go back to my main script, now I'm just going to call this Exponential Script. And so then basically I should be able to come to main.m, press play, and then just have 16 figures to go and look at. If they're, basically sines and exponential functions, then you win. And there you go. That's what it looks like. So that's the sort of thing I'm looking for. It doesn't have to be quite this organized, and even this isn't all that organized. But basically, just if you just have basically sine, what I have here for sine script, and then just immediately underneath this you put the square root, and immediately underneath that you put the exponential function, and then I can just push play on one file that you will call main.m, then I'll be happy. And that way I don't have to go hunting through your code to see everything. I can just see, okay, immediately I get an impression that you did all that correctly, and then I can just go quickly take a look at individual files to just make sure you did everything else right, and then ta-da, you get the points. But yeah, the one challenge that I really left you guys was to do the Lagrange interpolating polynomials. But again, if that doesn't work out, you can't figure it out in time, you have the other interpolating polynomial code, which will hurt your grade a little bit, but not terribly. Really, I just want to make sure that you want to get all this together. Again, if you aren't sitting at home playing the MATLAB code and coding along with me whenever you have to watch one of these episodes, then you're hurting yourself. MATLAB can only be learned by doing MATLAB. And so if you're in a freak out because you don't know how to code MATLAB, I'm guessing you haven't been going through and doing these coding sessions line by line as I'm doing them. Because that's the only way that you're going to do it. Just like taking notes in class, and just like doing homework and practicing, you can only be successful if you practice this stuff. And so, yeah. So if you've been having a lot of issues with that, with the code and understanding what to do, it's likely that you haven't been coding as we've been going. And the way to rectify that in the future is to code as I do. It'll take a lot longer, but it'll help you sort of assess what's going on in MATLAB as you're going. That is the whole reason why I'm coding this line by line for you guys as I go. This one I sort of already had set up just because I wanted you to see what the final project would look like. I didn't want to code up everything right in front of you because, well, I want you to answer some questions and face some challenges without me holding your hand there. In any case, hopefully this helps, and hopefully this clarifies things for you. And if it didn't, please email me and we can talk about it. And yeah, I'm available through email if you want to get hold of me. I've helped 1 or 2 students figure out where they're stuck with their code, and yeah, that's what I'm here for. All right, thank you for watching, and yeah, I hope this helped. All right, bye bye.